Finding eigenvalues and eigenvectors, right? How do we find the eigenvalues?
You need to get zeros from the bottom three quarters, quarters.
Zeros on the bottom and top.
Yeah, like the left three, so like the others are diagonal. Not sure if it's that.
We don't need to row reduce yet. We will. I'm going to find the eigenvalues. You've had one, so I know you know. What do you have to do?
With the lecture,
With the what?
lecture.
Or how do you get them? Those are your eigenvalues. You didn't have me for one year, so I can't come and change your grade now.
Find the characteristic equation.
Which is what?
The determinant of A minus lambda I.
That's not an equation, that's an expression.
Yeah, equals 0.
Equals 0. It's the roots of your characteristic polynomial, right? What's I? More specifically, of the appropriate size. In this case, it would be a 3 by 3, right? So we have to take that determinant. Oh, well, that's nice. This matrix is what's called triangular. Specifically, this one is lower triangular, but it doesn't matter if it's lower or upper. If you have a triangular matrix, the determinant is just the product of the terms along the diagonal. Right, so a triangular matrix is just a matrix that has either all zeros above the diagonal or all zeros below the diagonal. Lower triangle is if the zeros are above, upper is if the zeros are below. Again, for determinants, it doesn't matter which one, as long as it's triangular. That is an easy system to solve. Four and one. But 4 repeats. That is called its algebraic multiplicity. So 4 has an algebraic multiplicity of 2. Finding the eigenvectors. Remember, just take your eigenvalue, plug it back into your matrix, and then you row reduce that. minus 1. 4 minus 1. Oh, that is nice. We already get a row of zeros, which makes the row reduction here really easy. That's the interpretation of that matrix. X1 is 0, 3x2 is 0, 0 equals 0. X1 and X2 both have to be 0. What about X3? It's a free variable, it can be anything. Except for 0. Eigenvectors can't be the 0 vector. We just want one eigenvector, right? Zero, 0, 1. There's an eigenvector. Not 4. Technically, I actually should have made that 3 a 1 there, but it doesn't matter. Just like here, I should actually make that this. Flip to rows. Row 2 to row 1, and then row 3 to row 2. eigenvector be of that form. Zero, 1, 0 would be your only eigenvector. For now, that's where we're going to stop. For the purposes of what I need to do for differential equations and variable keep going. No, stop there. Again, all eigenvalues and an eigenvector. That is again triangular. It's just a product of the elements along the diagonal. You get lambda equals 2 with an algebraic multiplicity of 3. We plug it back in. 0, 1, 0, 0, 0, 1, and then 0, 0, 0, which is already row reduced. So you get 1, 0, 0.
What does that 1, 0, 0 represent?
That's the eigenvector.
Where does it come from?
x2 has to be 0, x3 has to be 0, right? What about x1?
I don't know.
Can be anything.
Okay.
Alright, so I just didn't write it out in that form this time. I didn't show what they all would all look like, just pick one. So since x1 can be anything except for 0, I just said it's 1.
And then x2, like where do you look to get that? And x3 too.
That's x2.
Oh, okay.
And then column 3 is x3.
So the iodized columns,
Not the list. I can write something that.
sorry.
Plug it back into here
Eigenvectors is one.
and then solve the system.
So then they come from the column.
Row reduction. Row reduction, and then you look at each column. This first column represents the coefficients of x1, the second is coefficients of x2, third is coefficients of x3. This is another triangle, which is nice. Which means for the sake of time, I won't write out the determinant we're taking. Should see it when you get 3 minus 10 to the 4th power equals 0, right? Lambda equals 3 with a multiplicity of 4. Yeah, that needs one matrix, which is nice. Zero, 1, 0. 0, 0, 1, 0. And 0, 0, 0, 1. That is again already in row reduced form. x2, x3, x4 all 0, x1 is anything. One, 0, 0, 0 would be an eigenvector.
Is this on the exam?
This will be it.
Okay.
Finding eigenvalues, eigenvectors.
It's like x2 and eigenvector.
No, these are for systems. Which is why I don't have the arrows over them.
Can you point out how you get x2, x3, and so on?
That's x2.
The one?
That column represents x2. Each row is an equation in the system. Each column represents the coefficients of a specific variable. First column would be x1.
So your
Second column is x2.
Okay.
So the first equation is 0x1 plus x2 plus 0x3 plus 0x4 equals 0.
Okay. And when you declare 0 equal to 0, that's just.
That's because that's just 0 plus 0 plus 0 plus 0 equals 0. That's what this row represents as the system. So this is the corresponding system to that matrix.
And when we say x1 equals the column in right,
This is the eigenvector itself.
eigenvector, so the one comes from,
x1 is a free variable.
so it can always be 1?
Little x1 is a free variable. can be anything except for 0. So just pick it to be 1. Because they only want one eigenvector.
That's a always type of thing though, or is it just certain cases?
No, your free variables, you can always let them be whatever you want,
Okay.
aside from always getting a 0 vector.
Where did the 1 come from in the second column?
Here.
Yeah.
Oh, I have the wrong matrix. That should be 0. Oh, that makes this interesting, huh? You have 2 free variables.
In the matrix you just did right now, you just switched the rows.
To put it in the row reduced form, all the zeros have to appear at the bottom.
Okay.
What's the procedure to get to that?
I just flipped row 1, row 2, and then row 3, row 2.
And you can just flip any of them.
That's one of the elementary operations. You can just flip any 2 rows.
Do they have to be side by side or
Nope.
just any?
Nope, any of them.
Okay.
Just pick 2 rows, flip their positions. That's always allowed.
So then x3 equals 0, but there's a 1 in column x3. So how does x3 equal
Right.
0?
So this is the first equation in the system. 0x1, 0x2, 1x3, 0x4.
Mm-hmm.
That's just x3, and it equals 0.
Which is x3?
That column represents the coefficients for x3.
So because there's the 1, that's indicated.
It's 1 times x3. Right? Each row is an equation in your system. Each column are the coefficients of a variable.
So let's say there was a number, let's say 2. in
It'd be 2x3.
row 3, column 3. It'd be x3 equals 2.
Right here. 2x3 equals 0.
2x3 equals 0.
Because it's homogeneous, it's always going to equal 0.
And x4 equals 0 because,
Because of that right there.
and the other two don't have anything because there's no
Right, because
value greater than 0.
it's all zeros in the first 2 columns.
Okay.
This one I wrote right out, actually. X1, X2 can be anything as long as they're not both 0. 1 can be 0. One of them can be 0, but not both of them. Otherwise you get the 0 vector, which you can't have. The easiest 2 eigenvectors would just be, say, x1 is 1 and x2 is 0. That gives you one of them. Then x1 is 0, x2 is 1. There's your second one. So we get 2 eigenvectors out of this one.
So in this case, it's on set one of the x's to zero because the whole.
You can have- You can't have all of your free variables being zero at the exact same time. Or if you have three, two of them can be. Right, as long as they're not all zero. Yes. And we'll be doing, like I said, a lot more of this, solving systems. Greater short.
I've never given this for guidance.
Yeah. So, we have gotten this exactly correct.
Similar stuff.
Yeah, we're not gonna have a long break. We can- run over.
What do you think yesterday? Did they open it at least?
I don't really care. Yeah.
But like, for us, we'll open notes and put it where we're open to discussion.
This is what I had, apparently it's first time looking at this, so I think it's just kind of doing whatever.
Yeah, that's beautiful.
Wow, these are- I guess.
Now the fun begins. So in general, if you're given a system x prime equals ax, we're looking for a solution of this form. Right? Some constant vector times e to the lambda t. And then sum them all up. If you have distinct real eigenvalues, and it'll just be your eigenvector and eigenvector times e to the lambda 1t. That would be one solution. Right? Then your second solution will be based on your second eigenvalue, be an eigenvector for that times e to the lambda 2t, so on and so forth. It's that easy. If it's repeated, you get two possibilities. So let's say it's multiplicity m, your eigenvalue. You get two possibilities. You either get m linearly independent eigenvectors out of it, or you don't. If you do, you're fine. Because then your solution would just be C1, one of the eigenvectors, e to the lambda t, plus C2, another eigenvector, e to the lambda t, so on and so forth. You get m linearly independent eigenvectors, you get m linearly independent solutions. If you get less than m eigenvectors, we have to find additional solutions. That's a nightmare. It's actually not as bad as it looks. This looks really intimidating. it's not as bad as it seems. And then your third case is you get complex eigenvalues. So you have lambda is alpha plus beta I, and lambda 2 is its complex conjugate. Right, so alpha minus beta I. Right, we get two solutions out of that. Lambda 1 e to lambda 1 t, and the complex conjugate of lambda 1 times e to the complex conjugate of lambda 1 t. But those are complex valued functions, not real valued. So we write them in terms of real valued. We're working down. Working down, we're going to have a B1 and a B2. Those are important to keep in mind. These are the two solutions that we'll wind up with. B1 cosine of beta t minus B2 sine of beta t e to the alpha t as one solution, and the other solution is B2 cosine of beta t plus B1 sine of beta t is equal to e to the alpha, or times e to the alpha t. Instead of remembering B1 and B2 this way, we can also do it as B1 is the real component of your complex eigenvector. B2 is the imaginary component of your complex eigenvector. So again, this looks all really intimidating, but it's really not. It's not as bad as it looks. Find the general solution. First thing we're going to do is write this in matrix form. I'm going to call it right, so I'm going to say that my capital X vector is just this. Right, then we'll have X prime is equal. Remember, each row represents an equation. Each column is the coefficients. First column, coefficients of X, 2, 1. Second column, coefficients of Y, 2, 3. That is your coefficient matrix. And that's just times X, right? Because then it's just times X, the vector X, right? There's the matrix form. Step 1. Is to find your eigenvalues. Remember, that's this determinant. Now, we're not going to do this by hand. For this problem, I'll show you how to do it in calculator, and then afterwards, I'm just going to use Wolfram. Menu. Matrix and vectors, determinant. Now there's two ways to form a matrix. Menu 7, create 1, and then matrix 1. It'll then ask you how many rows and how many columns you have. Now you just enter the entries. Or brackets. Oh wait, you can't even bloody see my screen. I thought I actually switched. Start over. Right. Menu, matrix and vector, 7, predeterminate. Menu, matrix and vector, create matrix. 2 by 2, and then you just put in your entries. Or control right here opens up brackets. Entries of the first row separated by commas. 2 minus lambda. I'm going to use x because it's just too much of a pain in the ass to put the lambda character. Comma 2. That was the first row, right? You separate columns with a semicolon. Oh, I'm sorry, you separate your rows with semicolons. So now it's the second row. It was what? 1 and then 3 minus x. There's the matrix. And if you notice, it'll automatically put it in matrix 1. There's your determinant. All this is saying is that the domain of the result might be different than the domain of the input. So you can just ignore it. That has to equal 0. I'm also going to use a calculator to solve it. Menu algebra solve. I can go ahead and just copy that. The determinant equals 0 for x. 1 and 4. Notice we have distinct. Now, if you're feeling really bold, not reduced, advanced. You can just use the eigenvalues feature on the calculator. I would, however, recommend you do not use the eigenvectors feature, as that can be a little bit wonky.
Does it not This one.
Now, it should do it, but it's a little wonky. Advanced.
Oh. Those 90s.
It uses a very weird process to find the eigenvectors. Yeah, no.
Guessing you wouldn't accept that as an
I mean, technically those are eigenvectors, but have fun. Next step is to actually find the eigenvectors. Because we already know what our general solution form is going to be. C1, an eigenvector for lambda 1, times e to the lambda 1t, plus C2 times an eigenvector for the second eigenvalue, e to the lambda 2t. So now we just want to find those eigenvectors. Process is the same as what we've been doing. Go back to your matrix, 2 minus lambda, 2, 1, 3 minus lambda, and just plug in each of the eigenvalues, right? So let's start with 1. So you should get that. Arc already knows that that's going to row reduce to. So it's obvious. If you have not had linear algebra, I would recommend you do this. Oops, not on this one. I would define a matrix M of x so that you don't have to write out a matrix multiple times. Because now we can just do this. Ready? Menu, 7, reduced row echelon form, n of 1. Right? Our first eigenvalue is 1. Yes. And actually, I need to reverse this, sorry. Forgot my notes, I did the other order. So there shouldn't be negatives, those should all be positives. You'll get x1 is negative 2x2, and x2 is any real number. Negative 2 comma 1 is an eigenvector, right? There's the eigenvector I'm going to use. And let's call this x1 star. There's your first solution vector to the system. Right, it's the eigenvector times e to the 1 times t. Now we need to find the second one.
Is that x1 to the x? What is that little?
That's a star.
Oh, it's a star.
And again, I'm just calling it that as my first solution vector. Because I just used x1. Repeat the process now for lambda equals 4. If we plug in 4, we should get this, right? Make sure my signs were right this time. And we want to row reduce that. Again, if you've had linear algebra, what that row reduces to is very obvious. For those who haven't, just go back to your calculator. I'm not going to do the menu this time. I'm just going to go RRPF M of 4. And there's your row reduction. This gives us an eigenvector of 1, 1. So the solution vector would be 1, 1 times e to the 4t.
And you just chose 1, 1 because they're greater than 0.
But it doesn't necessarily be greater than 0, just can't be 0.
Oh, okay.
Right? You can't get 0, 0 as an eigenvector. But outside of that, you can let x2 be whatever you want it to be. Then the final step is your superposition principle. And there's your solution.
So why isn't it there wasn't a 0 in the previous one? Oh, because there's 2 persons.
I'm going to follow a general principle, which is since the equation was originally given to us, not matrix form, I'm going to write my solutions, not matrix form. And again, I could go even more general and say that negative 2c1 is some new constant, c3, if I wanted to. But I'd just leave it in that form for now.
So then depending on the size of the matrices you're working with, is how many matrices you're gonna get. So how many rows there are to be.
The number of rows tells you, I'm sorry, the number of rows tells you how many equations you have. Number of columns tells you how many functions you have. But for this method to work, it has to be a square system. So you have to have the same number of equations as you do unknowns.
So would you ever have something that was like, in this case, the 1 by 2, and could you have like the 2 by 2?
What do you mean?
Like, would you ever have like a 1 by 2 matrix, but you have to plus a 2 by 2 matrix?
Well, you can't do that at all. 1 by 2 plus 2 by 2 is undefined. What I'm talking about is the original system. You have to have the same number of equations as unknowns for this method to work.
So because here x and y are unknowns,
Yes.
you wouldn't have.
Right, so your system involves x dot and y dot. I'm pretty sure that doesn't necessarily have to be the case, but for this class, that's always going to be the case. What does this give me? Yeah, why not? We'll do this one, and then I'll look to make sure that we get at least one of each of the cases when we look at the matrix forms. Distinct, repeated, and complex. Again, let's write this first in matrix form. Coefficient matrix. First column. (250). Second column. -7, 10, 5. Right, coefficients for y. Third column. 0, 4, 2.
So is there a reason that you call the matrix vector x prime?
I'm saying x is just the vector x of t, y of t, z of t. Right, then obviously if you look in the left-hand side of the equation, the x dot, y dot, z dot, that would just be x prime. No space there. Step 1, find your eigenvalues. Let's set this up in Wolfram. Oh good, there is an actual eigenvalues command. I've never used it in Wolfram. Here's what I'm going to do. I'm going to define a coefficient matrix, A. To enter a matrix in Wolfram, the entire matrix is in braces, and then each row is in its own set of braces. We said it was what? 2, -7, 0. And then you separate rows by a column. There's my matrix. I'm also going to define matrix M of X as A minus X times 3 by 3 identity matrix. X is my eigenvalue. Let's go and do those. Alright, so I'm going to do both. I'm going to go solve, determinant, mx equal to 0 for x. I need to put there. And again, let's put that in table form. There are your three eigenvalues. Let's see. What that gives me. Oh, cool, okay. Right, or you could just do eigenvalues of A. Right, however bold you're being, however much work you want to show me. Right, this is not a linear algebra course, so I'm not really testing if you know how to find eigenvalues. I'm testing applying them. Either way, we get 2, 5, and 7, right? That's fine. I don't care. Now, step 2, find eigenvectors. Again, you have 3 distinct eigenvalues. For the sake of space, right, I will not do it the way I did it before. Why is my pen not working now? There we go. So I won't write out each matrix that we're row reducing. Again, depending on how much work you want to show me. So here's what I'm going to do in Wolfram, I think. Print. And actually, I can just copy and paste. What's the other one? 5? Seven. Right, so when you do eigenvalue 2, this would be a row-reduced matrix to look at. Right? Eigenvalue 5, there's the row-reduced matrix. Eigenvalue 7, there's the row-reduced matrix. Well, look at what this first matrix is saying. X2 is 0. X1, negative 4/5 X3. Right? Oh. So why don't we do 4, 0, 5 as an eigenvector? I'm sorry, it wouldn't be 4, it'd be negative 4. Negative 4, 0, 5. Because X, but you know that your second entry is going to have to be 0. And you know that your third entry is going to be your free variable. So let's look at 5. Once again, column 3 doesn't have a leading 1. That means x3 is going to be the free variable. Well, based on the fact that these are both fifths, I'm going to set x3 to be 5 again, just to clear out the fraction. Then it would be what? -7, +3. 7, 3, 5. No, -7, 3, 5. Once again, x3 is the free variable. I have 7/5 and a -1. Okay, so I'm just going to let it be 5 again to clear out that fraction. Looks like it's going to do what? -7, 5, 5. Then just write out your general solution. C1 times x1 e to the lambda 1t. Lambda 1 was 2. Right, because that was the eigenvector associated with the eigenvalue 2. Plus C2, -735. E to the 5t. Plus C3, -755. E to the 7t. There's the solution in matrix form. For this one, I will just keep it like that. Let's see. Oh, nice. Okay, this one can be repeated.
How did he get, like, roll from x to be 0? In the eigenvector, how do you get x to be 0? You go back to the whole matrix. See this, like, x1 equals 0, x2 equals 0, and there's
X1 doesn't equal 0. X1 plus 4/5 x3 equals 0.
other than that.
It always goes by row when you're doing the equations. Then x2 equals 0. And this just says 0 equals 0, so it's redundant. You don't need it.
Okay.
General solution, is still a system, right? It's just already in matrix form for you. Coefficient matrix, already given for you. That's what we need to find the eigenvalues of. So again, what I'm going to do is define two matrices, the coefficient and this time the identity matrix is 2 by 2. And so let's define those two matrices right off the bat. I'll go ahead and just use eigenvalues because I'm lazy. Oh, that is so nice that it actually listed out more than once. I didn't know it would do that. This gives us one eigenvalue, 2, right? But it's repeated, so it has a multiplicity of 2. That means we have two possibilities. You will either get 2 independent eigenvectors out of it, or only 1. If we get 2, we're fine. If we only get 1, oh, then we have to deal with that hideous looking formula. So let's see which one we get and hope for the best. And actually, if you've had them in your algebra, you know what case we're going to have. You only be able to get 1 out of it. That'll just be what, 1, 1 of the eigenvector? We need to get a second eigenvector out of that. I call it, it's not really going to be an eigenvector. The goal is we're going to get a second solution out of that. Here's what we're going to do. I'm going to start by finding a second vector. I'm not calling it eigenvector because it's not going to be an eigenvector. And I'm going to do that by solving that equation for x2. And this is why I said the order now matters. For this technique, it has to be A minus lambda I, not lambda I minus A. What was into... I'm too lazy to do it in my head. Negative 3, 3, negative 3, 3. Oh, that's actually what I have in my notes. Oh, I actually took right in my notes. I'm shocking. What do I want to call this? Oh, let's call it Y1, Y2. Why not? I might actually just do that right in. I just used stock command. I just literally plugged in the matrix equation to solve for Y1 and Y2. It's giving me Y2 as a function of Y1. So they make Y1 the free variable here. Yeah, that'll work. I only need one of them, so. Say y1 is 0, y2 would be 0 plus a third. So 0, 1/3 can be my coefficient. X1 star is just the same. Second solution. Pretty sure it's going to be this. I'm going to write it this way though. Writing it that way because if this was a 3 by 3 and there was a multiplicity of 3 and only got one eigenvector out of it, I'd have to repeat the process. Except for the third time, it would be t squared over 2 factorial. Right then, plus, it would be the x1 times that, plus x2 times the te to the t, or whatever the value is, plus x3 e to the t, right? And then if you had to do, let's say it's multiplicity of 4, you had to find the fourth one, t cubed over 3 factorial would be t cubed over 6. Those are your two solutions. Now use superposition. It's C2 times the entire X2 solution. That. There should be 2 T, shouldn't they? That's the solution. Right? Or you may commonly see it written that way as well. Okay, the goal is you don't have repeating, right? So I don't want an e to the 2t to appear in both, which we don't. Right? It's a t e to the 2t in the second one, and a t plus a third e to the 2t in the second one as well for the y. That one later. I'm going to skip to this one for right now because this will give me complex eigenvalues. And then if I have time, I'll go back to that one because that will give me one that has a eigenvalue multiplicity 3 with only one eigenvector. But I definitely want to get a complex one done. Oops. Right, this time A is not that. There's A. Three I and negative 3I. Oh, this will be fun, won't it? I'm also just going to go ahead and do this. Now, I only need to do one of them for our technique. So I'm going to do the one that has the positive imaginary component. That is the custom, use that one. So you could do what I just did there. So I hit escape, double I, escape. I think you can also just do capital I. I think capital I is the imaginary number. Let me just double check that. Yep. There's our reduction. So I'll write all that out right now, and then I'll show it on screen. Right, move this. Those will both be positive, right? X2 is free. So I have the fraction, call it 5. Then you have 4 plus 3i is x1, and x2 would be 5, right? Which gives that. Rewrite that. Into a real and imaginary, right? The method says this vector is B1, this vector is B2. Now if we go back to the derivation, theorem 2, this will be our two solutions. All right, we know what B1 is and we know what B2 is. Remember, alpha is your real component of the eigenvalue, or our eigenvalue is 3i, right? So what's alpha? What's the real component of 3i?
1, 0.
0. E to the 0 is 1, so we're not going to have the E. What's beta? 3. So the two solutions we get, you don't actually have to write out both solutions. I'm just doing it. X1 is B1 cosine of 3t plus, no, I'm sorry, minus, right? Minus B2 30 sine of 3t. X2 is B2 cosine of 3t plus B1 sine of 3t. The general solution C1 times this plus C2 times that. Which is this. So again, typically what we'll do is we'll write the two cosines together and the two sines together. There are two ways to represent that. That's to write your actual unknown constants together in the vector, so that you just have two vectors. Right. Otherwise, you would have this. Which doesn't look as clean as this. But they're both valid. Or you could just do C1 times that whole thing plus C2 times all of X2 and leave it like that if you wanted to. But that would be even longer.
How did you go from the row reduced form to the eigenvector?
So in my head, this says that x1 minus, this is the coefficient, x2 equals 0. So x1 equals 4/5 plus 3/5 I all times x2. This is 0 equals 0. So x2 is a free variable. I set it to be 5 to clear out the fractions. Right, then you have 4 plus 3i all times, or sorry, just that is x1.
Could you write that out if you have time?
Let's copy that. Putting that here. So I have that reference. That's the equation, right? First equation solves to that, right? And x2 is any real number. So I've just set it to 5, because it'll clear out the fractions. But that's what it is.
Okay.
Right, and then from there you should see how I got that. 3 plus I, or 4 plus 3i, 5 is my eigenvector.
Got it. So the 4 plus 3i is x1 and the 5 is x2.
Yes.
Okay.
Now, unfortunately, I'm not going to have time to do it anymore. It's going to take me way more than 5 minutes. With the aid of the calculator, right, it's still a long process, but at least you're simplifying all the calculations. Use your calculator. Do not try and do this by hand.
Can you show how to find the eigenvalues on the calculator again?
Oops, that's the wrong one. That's the wrong one. That's on screen. That's what I wanted. It would be menu 7, all the way down, advanced, which is B, for eigenvalues. Once you get that, you're then going to have to enter a matrix. Right. Easiest way to create is probably just go again, menu 7. Create 1, and then 1. Tell it how many rows, how many columns. I'll just go 2 by 2, and then you just enter each component.
And you'd use x instead of that.
No, if you're using the eigenvalue itself, you don't need to worry about the x. Just enter the coefficient matrix.
Okay.
If you don't want to use the eigenvalue, and you want to do it like this by with the determinant, then you can use whatever you want for the eigenvalue. X, again, I use X because it's the easiest thing to find on the calculator. It's more of a pain to go to lambda, but you can use whatever you want.
Okay.
collected on the 24th. Remember, as I said, since the stuff that we just did, I forgot to include on the exam. I won't be collecting those homeworks with this second journal, but those homeworks were next week. The homework journal assignment 10. So just do what's up there for this week, up to sections 10.1, 10.2, and 10.3. That's all I'm going to collect up to that for this test. Quiz 4 will go up after next class. Again, I'm pretty sure I forgot to include this stuff, which is sections 10.4 and 10.5 on the quiz. So I think the quiz will just go up to 10.3, which is the finding eigenvalues, not actually solving the systems. And same thing with exam 2. The exam 2 is not going to actually involve solving homogeneous systems. It'll just go up to finding eigenvalues and eigenvectors, not actually applying it. And that will be next Thursday. I also forgot to mention last class, but the second exam bonus is up, and that will also be due before the exam on the 24th. Same as last time, up to an extra 6 points on the exam score.
Do we still get those 3 points from the, like the,
When I grade them, yeah, that'll also be added in. I don't think you were here for that. I'm just deriving that auxiliary equation from 4th degree Cauchy-Euler. Yeah, that'll also be in there. So you can get a total of 9 extra points, right, if you get perfect on both. Next class on Tuesday, first 30 minutes will be the worksheet on this. 5-minute break. Then the rest of the class is the exam 2 review worksheet. If you paid attention on the first exam, the worksheet is a really good indicator of what the exam is. And so study that, and I do post the solution. So use the worksheet, use that review time as a good indicator of what's going to be on the exam. Thursday, first 100 minutes will be the exam itself, 10-minute break, and then we start solving non-homogeneous. Again, use a calculator. We're not using calculators a lot, because that involves inverse matrices and matrix products and integrating matrix products. Oh my god, it's awful. We'll make it so much easier using form. That's the layout for next week. Have a good weekend.
Oh, yeah.